In this class, we will discuss about the lateral stability of beams. So, in the last class, I have explained about laterally restrained beams with some examples. So, here we will see how a beam can be laterally stable. So, here I take an example of an I-section. I-section beam is hot rolled steel beam, which is normally used in the design of beams. Neutral axis will be there here. I have taken a symmetrical I-section. If you take the longitudinal section, assuming it as a simply supported beam, the top fibers will be subjected to compression and the bottom fibers will be subjected to tension, and the deflection will take place like this. Flanges will deflect like this. So, on the other way, if this compression flange is not supported or restrained, if it is unrestrained, then there is a possibility of both the horizontal deflection as well as the vertical deflection of the beam when it is subjected to load like this. So, horizontal deflection is measured like this. In the plan, you can see that lateral deflection can also be called as horizontal deflection, and vertical deflection is like this. So, that means when the compression flange of the beam is not supported or restrained, when it is unrestrained, so the beam will be subjected to both vertical and horizontal deflections. And in plan, you can see like this. Sorry, not in plan, of course. In plan, of course, you can see like this. You can have a twist also. So this is the lateral deflection. So initially, the beam is here. It deflects like this. So lateral deflection will be like this, and there will be an angle here. Twist also will take place, which means it is subjected to torsion also. So that means a combined effect of torsion and lateral deflection will take place, and that is called as a lateral torsional buckling. So that phenomenon is called as lateral torsional buckling. That is why normally in the case of design of a beam, we choose a section in such a way that this moment of inertia about this ZZ axis is always greater than moment of inertia about this YY axis. So because YY axis normally becomes the weaker axis, and this is the stronger axis. So moment of inertia IZ will be kept more than IYY. And this is the direction rotation we are going to follow in the design of beams. X will be along the length of the beam, Z will be along the horizontal axis of the cross section, Y will be along the vertical axis of the cross section. Now we are going to define an important term called elastic critical moment in the case of laterally unrestrained beams. It is defined as MCR, it is defined as the bending moment at which a beam fails by lateral buckling when subjected to a uniform moment. So this is the ultimate moment that beam can take when it undergoes lateral buckling. So that is the word. Of course, we are going to use one word called moment of resistance in the case of pure bending of beam. So it is of course similar to that. So when the beam is subjected to lateral buckling, at that time, whatever bending moment is there on the beam, that is called as the elastic critical moment, denoted by MCR. CR represents the critical moment. And as you know, in the theory of torsion, circular sections they will not be having any warping. We have studied that in your electricity also. Whereas I-section, normally I-sections with plates or channel sections, they are used in the case of design of beams. In that case, these I-sections will be subjected to warping effect. So this is a warping effect is nothing but out of plane bending or out of plane deformation, that is called as warping. So in addition to twisting, warping also will be there. So this warping will take place due to the rotation of the beam cross section. So rotation of the beam cross section will take place in the case of I-sections when it is subjected to twist. So that effect is called as warping effect. So there is a formula to calculate the critical elastic critical moment MCR. So we can derive this. So anyway, so this is the formula pi by L into root of E into I y into G into IT plus pi E by L whole square into I into P where this E is the Young's modulus of the material, that is steel, and G is the rigidity modulus of steel. Iy is the moment of inertia about the weaker axis, that is YY axis, or we can call it as minor axis, whereas It is called as the Saint Venant's torsion constant. Saint Venant's torsion constant. So E into Iy is called as the flexural rigidity, which is in Newton mm square, whereas Git is called as torsional rigidity, which is in Newton millimeter square. It is the Saint Venant's torsion constant, which will be in millimeter power 4, and Iw is the warping constant, which will be in millimeter power 6. And N is the unraised length of the beam subjected to constant moment in the plane. So, or you can say unraised means or unsupported. You can take it as unsupported, unrestrained, like that. So, these are the notations which are used in this formula. Once you know all these values, you can compute that value of elastic critical moment for that particular section by knowing the length. Now, here, example for a symmetrical I-section. Symmetrical I-section. This is symmetrical I-section. This is Z axis. This is Y axis. BF is the width of the flange. TF is the thickness of flange. H is the total depth. Total depth of that I-section. So in that case, the values, you can remember these values for a symmetrical I-section. You can get Iy value as BF into TF cube by 6. IT value is 0.9, BF TF cube, and IW as Iy into h square by 4. So these are the formula we can derive for these three values. Then substituting this here by knowing E value, L value, we can find out the MCR for that particular section. So this is a simple concept of unrestrained beam. So lateral stability of the beam can be achieved by supporting the compression flange of the beam, which I had explained in the earlier lecture. So here actually what I mean to say here is, when the beam is laterally unrestrained, then it is subjected to both torsion as well as lateral deflection. That is one thing, and warping will take place. And in that case, we will be having a value of MCR. MCR value will be there, which is not there in the case of laterally restrained beams. That MCR value is computed using this formula. And for a symmetrical I-section, these three I values are obtained using this formula.